New tasks for aerial robotics, such as package delivery, agricultural inspection, and warehouse inventory management, require confident operation near structures and people. That degree of precision and control in state estimation relies on accurate dynamical models and effective use of limited onboard sensing. In this work, we focus on how to estimate online the mass, center of mass location, and inertial tensor of a quadrotor. We show these parameters are observable from only motor command inputs in IMU and motor speed measurements. As a result, applying these ideas doesn't require any hardware not already present on nearly all quadrotors. Our approach is to develop an unscented Kalman filter that properly incorporates the commonly neglected second-order rotational dynamics. Critically, modeling the net aerodynamic moments due to the rotor's differential lift improves the accuracy of the state estimates. In addition to estimating inertial parameters, the UKF accurately estimates the aircraft true wind speed in experiments, once again using only IMU data. Knowledge of the weight, center of mass location, and principal moments of inertia of a quadrotor are fundamental to precise flight control. For a toy or a surveillance drone, the out-of-the-box parameters are easy enough to determine offline. Even for a reconfigurable drone, the center of mass location and inertia tensor are no longer constant, but we might be able to cleverly recompute them online from known design kinematics. But now consider the challenge of package delivery, or moving around objects on a large worksite. We're dealing with payloads that are a large fraction of the total flight mass, have unknown weight, center of mass, and inertia, and we expect these parameters to change constantly as parcels are picked up and dropped off. Unfortunately, the quadrotor state estimators most common today are blind to these inertial parameters. The reason is that their rotational model is essentially kinematic. It is typical to treat angular rates from the IMU as inputs to a first-order kinematic process model, and not as measurements of second-order dynamics. In throwing out angular accelerations, we also lose the notion of rotational moments. In contrast, we first wish to work with a full Newton-Euler translational and rotational dynamics, and see what opportunities that opens up. In doing so, we find that just modeling rotor thrusts and drag torques as quadratic functions of rotor speed is not adequate. We must correctly model aerodynamic forces and moments on the vehicle, including their dependence on flight speed. Rotors generate nominal thrust that is a quadratic in the rotor speed, but in axial flight, the blade angle of attack is depressed and thrust decreases. This decrease in thrust appears as a drag-like term, which opposes the velocity component perpendicular to the rotor plane. Similarly, rotors in edgewise flight experience a net horizontal force, the so-called H-force, which opposes the direction of flight. This appears as another linear drag-like term, now opposing the velocity component in the rotor plane. These drag and drag-like terms can be combined to complete the translational dynamics of the aircraft, now including modeling gravity, the commanded thrust, and these airspeed effects. The rotational dynamics require considering three main sources of moment: the motor reaction torques in the yaw direction, the moments exerted by the rotor forces on their moment arms, and the direct hub moments due to rotor differential lift and flapping. The motor reaction torques are typically assumed to be quadratic in the rotor speed, but this is actually motivated by a quasi-static assumption that the motor reaction torques equal the aerodynamic rotor drag. In aggressive flight, we find that modeling the PI speed control effort yields a much more accurate and less delayed estimate of the true reaction torques, and as a result improves the quality of our Z moment of inertia estimate. The remaining two aerodynamic moments are due to differential thrust between rotors at high angular speed, and due to blade flapping or differential lift across a single rotor at high translational speed. The differential thrust between rotors comes from applying the aerodynamic force models from before to the rotor's moment arms. A large nose-up pitch rate causes rotors at the front and the back of the aircraft to experience different local inflow velocities. As a result, the thrust on the leading rotor is depressed, and the thrust from the trailing rotors is elevated. The net contribution is a moment opposing the angular velocity. In contrast, the net moment from flapping and differential lift is a function of the translational speed and is directed perpendicular to the airspeed velocity. The origins of this moment are a bit more subtle and often neglected, but is important for obtaining good inertia and velocity estimates. As a single rotor rotates in edgewise flow, the blades experience increased lift while advancing against the flow, and reduced lift when retreating with the flow. This aerodynamic forcing causes the blades to flex up and down and exert a restoring moment on the hub, and that restoring moment is the true torque on the airframe. The second-order cantilever dynamics cause this reaction moment to be somewhat out of phase with aerodynamic excitation, and be neither aligned nor perpendicular to the flow. What is interesting is that the net moment across the vehicle is perpendicular to the direction of flight, independent of any details of the aerodynamic parameters or blade stiffness due to design symmetry. In fact, any multi-rotor where the center of mass is at the centroid of both the clockwise and counterclockwise propeller should experience such a pure pitching moment in forward flight. From flight experiment data, we can easily discern the residual moment due to this translational velocity effect, and find that it is in fact proportional to the flight speed. Armed with our dynamic model, we can check the observability of the system. We're interested in the 32-dimensional state vector representing the aircraft tilt, angular velocity, linear velocity, the gyro and accelerometer biases, aerodynamic coefficients, and inertial parameters. Casting the dynamics into a control affine form, we can determine the system has weak local observability almost everywhere. An example of a degenerate state is a stationary hover. Intuitively, this makes sense. Some angular excitation is necessary to estimate the rotational inertia. In our experiments, we adopt Lissajous patterns using sums of sines. Long period changes excite large changes in velocity without saturating actuators. At the same time, short period components excite high angular accelerations, making it easier to estimate principal moments of inertia. The attitude estimates agree well with the ground truth. Recall that we're not using cameras or any other exteroceptive sensors, and so we can only estimate tilt, but not yaw. In spite of only using IMU measurements, the velocities remain close to ground truth with very little drift over 60 seconds of aggressive flight. Finally, we can return to the inertial parameter estimates. Motivated by picking up and dropping off packages, we estimated a set of inertial parameters for one flight with a bare platform, and then again after strapping on additional weights. These weights represent about a 20% change in aircraft mass and a 30% change in principal moments of inertia. The difference in estimated mass was accurate to within measurement error, and the final inertias were within 5% of the expected true value, or 20% of the value change. Adding rotation dynamics to the UKF allows us to estimate inertial properties of the aircraft and any attached payload using ubiquitous IMU sensors. No cameras or other exteroceptive sensors are required. By carefully modeling the aerodynamic force on the drone in fast forward flight, and at high angular rates, we can both improve the accuracy of these inertial estimates and additionally obtain accurate wind speed velocity estimates. And these speed estimates don't depend on cameras or GPS. Taken together, these new capabilities could power safe fallback options in camera blackout scenarios, allow for estimation of wind fields, or enable controller adaptation during package pickup and drop-off operations.